Welcome to Chapter 5 of Business Calculus, Integration. Integration is the opposite of differentiation, and we're going to see that it has a lot of really interesting applications. We are going to start by looking at integration as the antiderivative, or because it is the opposite. So, we need to review a little bit. Let's first review the power rule, the derivative of the exponential function, and the derivative of the natural logarithm. Remember, if n is not a 0 or a 1, then the power rule works for all other real numbers, and in particular for all the other integers. The derivative of x to the n is n x to the n minus 1. That means, I think, we remember that we multiply by the exponent and then subtract 1 from the exponent, as long as we have a polynomial term. But the derivative of the exponential function is itself the exponential function. This makes it a very important function in applications. And the derivative of the natural logarithm is 1 over x, or x to the negative 1 power. And this makes it important to fill out our table of derivatives. This table has ellipses at the top and bottom of each column. And that indicates that you can go as high or as low in either direction as you want to go. The derivative of x cubed is 3x squared, and x squared, the derivative is 2x. The derivative of x is 1x to the 0, or the constant 1. The derivative of a constant, like 1, is 0. The derivative of x to the negative 1 power would be minus x to the negative 2, and the derivative of x to the minus 2 power would be minus 2x to the minus 3, and so on. Notice we are always subtracting 1, not making it smaller, but moving to the left on the number line, and that the only way we could get the integer power x to the negative 1 on the right-hand column of derivatives is to include in the row the logarithm function, which again makes it important for applications. Alright, so let's look at computing some antiderivatives. Well, we know from Chapter 4 that the derivative of x cubed is 3x squared. And so we say that an antiderivative of 3x squared is x cubed. Right? In the last chapter, you were handed an expression and you were asked to give back the derivative of the expression. And now what we're going to do is give you the derivative of the function, and you're asked to give back the original expression. However, the derivative of x cubed plus 9 is also 3x squared plus the derivative of 9, which is a constant, so it's 0. So it's 3x squared. And so we say an antiderivative of 3x squared is x cubed plus 9. Now, we've seen situations like this before. The square root of 9 is 3, but it's also negative 3, depending on our situation. How many antiderivatives are we talking about? Well, let's take a look at our notes. So the power rule for integrals is found by performing the opposite of the derivative of a polynomial term. The derivative of x to the fourth over 4 would be 4 times x cubed divided by 4, and 4 divided by 4 is a 1, so we're left with x cubed. And the derivative of x to the fourth over 4 minus 12 would be the derivative of x to the fourth over 4 minus the derivative of 12, and so we have x cubed again. The derivative of x to the fourth over 4 plus pi would be x cubed plus 0. In fact, if c is any real number, it doesn't matter what it is, the derivative of this expression is going to be x cubed plus 0. And so all of these expressions have the same derivative. So we ask ourselves, what do the antiderivatives of x cubed look like? Well, they look like x to the fourth divided by 4 plus any real constant, because they all have the same derivative, x cubed. And we call this a family of functions because they all have the same derivative. All right, let's go back to our PowerPoint. And so we come to our first theorem, Theorem 5.1. If the derivatives of two functions are equal on an open interval, say the interval from 0 to 1 or negative 2 to 4, and on any interval from a to b, then they differ at most by a constant. Let's see if we can get a picture of this. These are all graphs of very similar functions. They're x cubed minus x plus some constant. X cubed minus x plus 0 is the lighter shaded one that passes through the origin. X cubed minus x plus 1, x cubed minus x plus 2, x cubed minus x minus 3, x cubed minus x minus 4. I can't graph all of them because then it would be a solid blue wall. But all of these functions, x cubed minus x plus c, are members of a family of functions because they all have the same derivative, 3x squared minus 1. Notice it has x-intercepts, or zeros, at, if we solve 3x minus squared minus 1 equals 0, we get x is plus or minus 1 over the square root of 3. So at roughly plus or minus 1 over the square root of 3, we have x-intercepts. If we graph both of them on the same grid, and here the derivative 3x squared minus 1 is in a dark red line, then you see where it crosses the x-axis, we have a maxima or a minima for all of the functions to the same points. And at the minimum for the parabola, x squared minus 1, in other words, when its derivative is 0, we have an inflection point for all of the members of the family of functions. So what's important to realize is that two functions belong to the same family if their derivatives, their slope, right, their instantaneous rate of change is the same at every point, which means they're going to look very similar in the graph. They're just going to be vertical translates of each other. If we notice the points where they cross, that's where we find the max and min vertically on every single one of these graphs. And where the parabola is at minimum, we find the inflection point for every single one of these graphs. So now we can change our table a little bit. The table still goes on, up and both down. But on the right-hand side, we have our simpler integer powers. And on the left-hand side, we'll have our family of antiderivatives. So the antiderivative of x squared would be something whose derivative is x squared, 1/3 x cubed, plus any real number, right? Any real number will give us an expression whose derivative is x squared. The antiderivative of x would be 1/2 x squared plus c. The derivative of a constant 1, x to the 0 power, would be x to the 1 power plus c. The antiderivative of 0 is not just 1, it's a constant, because if we had written it out 1 plus a constant, well, 1 plus an arbitrary number is another arbitrary number, so we'll just stick with c. The antiderivative of x to the minus 2 is minus x to the minus 1 plus c. The derivative of x to the minus 1, well, what function has a derivative that's 1 over x? Log x, or log x plus any arbitrary constant. So we see that we can build up the power rule in the following way. The antiderivative of x to the n is x to the n plus 1 divided by n plus 1 plus a constant. Now, it's important to realize that we're doing everything in reverse. Before, remember, we multiplied by the exponent and then we subtract 1 from the exponent. We have to do everything in reverse order. So we'll mess with the exponent first, because last time we messed with the exponent last, and then we'll divide last because last time we multiplied first, right? This is what we saw in our notes. To find the antiderivative of x cubed, we increase the exponent by 1 to 4 and divided by 4, and then remembered that expression plus any constant will do. Well, let's look at the antiderivatives of the exponential function. The derivative of e to the x plus 1 looks like the derivative of e to the x plus the derivative of the constant 1. So it's e to the x. The derivative of e to the x minus log 7, well, the natural log of 7 is just a constant, 1.945911049, on and on and on, but it's still just a constant even if it's an irrational number. So the derivative of the expression is the derivative of e to the x minus the derivative of a constant. it's still e to the x. And the derivative of e to the x is itself. So we ask ourselves, what do the antiderivatives of e to the x look like? They look like the exponential function e to the x plus a constant, where the constant can be any real number. What do the derivatives of the natural logarithm look like, and what do the antiderivatives of x to the negative 1 power look like? Well, the derivative of log x is 1 over x, or we can write it with exponent x to the negative 1. What's the derivative of log x plus 7? Well, it's the derivative of natural log plus the derivative of 7, which is 0. So it's still just 1 over x, or x to the negative 1. And so we ask ourselves, what do the antiderivatives of 1 over x look like? Well, they look like the natural log of the absolute value of x plus c. Again, c is any real number will do because they're all vertical translates of each other. So let's go back to our page. We have the power rule for integrals. Now let's look at the exponential function. The antiderivative of the exponential function is the exponential function plus a constant. The antiderivative of 1 over x would be the natural log of the absolute value of 1 over x plus a constant. All right, so some questions we still have that we want to answer in this chapter, and they basically boil down to, what is the derivative of an antiderivative look like? What if we combine them? What does the antiderivative of a derivative look like? This is going to be an important idea that we're going to look at in this chapter. And finally, if a basic function has more than one antiderivative, which one do I use to solve my problem? Before we go, I'd like to ask you a little quiz question. I'm going to ask you to give me a family of antiderivatives for an expression. Are you ready? Find all antiderivatives of the function f of t equals e to the t. Are they the constant 1, the natural log of the absolute value of t plus a constant, e to the t plus a constant, or none of these? Thank you.